Okay, so same thing with sample means. We're going to start, the difference here is you have quantitative data. So I have a population that I can actually graph on a histogram, which is really skewed to the right with a mean of about 8 and a standard deviation of about 1.5. If I take a sample of size 30, it's randomly selecting 30 from over here. There is the graph of my sample, the 30 individual dots. The x-bar for that is 7.9. Come over here and put a dot on 7.9. We can do that again. Make sure you see what we're talking about. There's another sample of 30, new graph, mean is 7.942, and both of those dots, sample means, are now on the graph, and the mean of the sample means is 7.921, and now you have a standard deviation of 0.029. Notice, this is a good time to look at something. This is the graph of the original population. This would be mu. This would be sigma. There's 18,000 dots on here, supposedly, one for every unit in the population. This would be the graph of the one sample of 30. So there's 30 dots on it. Every dot represents one unit from the sample, and that has a mean and a standard deviation and a shape very similar to the original population. This is the graph of the sampling distribution where every dot is the mean of 30, and now you're talking about the central limit theorem. So the mean of all the possible sample means should center at the original mean, close enough, but the standard deviation is significantly smaller. So keep that. That's a nice picture to see the difference between population, one sample, and all possible samples, or sampling distribution. So we're going to change the number of samples to get the 500. Take that off so I can see it. Again, mean is very close to the population mean, standard deviation significantly smaller, and we'll go back and look at that formula and relationship, and if you overlay the normal distribution, you can see the graph is approximately normal. So if you bring that back to your notes worksheet, central limit theorem for sample means describes the sampling distribution, so the shape is approximately normal if and only if n is at least 30, or if you're drawing from a normal population, small samples look like their population, your sampling distribution will still be approximately normal. The mean of all the sample means is equal to the population mean, and since the standard deviation is smaller, you know the formula. The population standard deviation divided by square root of n. So again, mean of the population was about 8. Standard deviation was 1.5. I took samples of 30, so the sampling distribution of the sample means for samples of size 30 will be approximately normal because n is 30, which meets the sample size condition. I don't care if the original population was normal because that condition is met. The mean of all my sample means will equal the population mean, which was basically 8, and the standard deviation would be equal to the population standard deviation over square root of n, which was about 0.27, I believe, in my calculator. So now if you want to go back and compare those answers to the computer simulation, the mean of all my sample means was, again, about 8. And I had a standard deviation of 0.266, which hopefully compares back to my 0.27, and it does. So again, there you have it. CLT describes that graph, shape, center, spread, mathematically, of all the possible x-bars, sample means, samples of size 30 from that population.